This app helps you to understand the multiple comparison problem. Multiple comparison problem is when you need more than just one test in order to accept or reject one single null hypothesis. Let me show you the details. What you see here, it's results of experiment where I ran a reaction using 3 different catalyst types, A, B, and C. Then you can see I made 5 runs for each catalyst, so I have 15 outcomes in total. And in this case, the null hypothesis is that there is no difference. So it means that average outcome, average yield for this reaction doesn't depend on which catalyst type you use. So it means that the average yield for the population is the same. And this is the true null hypothesis. This is the way I made this app, right? Now, how to test this hypothesis? For example, we want to use a t-test for that. But you remember that t-test, it's something that you can run only for 2 groups. You cannot run t-test for 3 groups. On the other hand, we can do it pairwise. So we can compare A versus B, and this is what you see here. You can compare A versus C, this is what you see here. And then you can compare B versus C, this is what you see here. So in this case, we run 3 t-tests in order to test one single null hypothesis, right? And this is the multiple comparison problem. What's wrong with multiple comparison running in this way? The problem is that you will accept null hypothesis only if you accept this one, you accept this one, and you accept this one. Only in this case where you have accept all three hypotheses, you will accept the original one. Why it's a problem? Because remember that when we accept or reject null hypothesis, we work with a certain significance level. For example, in this case, my significance level is 0.05. It means that I reject null hypothesis if p-value is smaller than this value, right? But if null hypothesis is true, then it means that in 5% of the cases, I will reject this null hypothesis incorrectly. So it means that I will accept null hypothesis only with 95% chance. But the same here, I will accept null hypothesis here only with 95% chance, because in 5% cases, I will reject it incorrectly. Also here, I will accept null hypothesis only in 95% cases. But the problem here is that I don't run just one test, I run 3 tests. So it means that I have a possibility to accept null hypothesis, which will be just 0.95 times 0.95 times 0.95, which is much smaller than original 95%. Let me illustrate this, right? So you can see that this is a single t-test I ran for comparing A and B. So in this case, the observed effect is 1.9. The t-value, it's a ratio between the observed effect and standard error computing, pooled standard error computing for these values. It's 0.4. It's a very small t-value, right? So it does not contradict with my null hypothesis about that there is no difference in the population means. And you can see that the p-value is 71%, so everything seems to be fine, right? So the p-value is large, the confidence interval crosses 0, so no problem here. Same here, so you have a observed small negative effect, but the t-value is very small, the p-value is large, so no problem here. Also no problem here. So every single t-test is results in a high p-value, and then we can accept the original null hypothesis, right? But what happens if we run it many, many times? So let me again do this little trick and run it many, many times. And then you can see that sometimes I have this rejection. You can see that, for example, in this case, both hypotheses are being rejected, right? So this p-value is smaller than 5%, this p-value is smaller than 5%, and so on. The problem is that I have 5% chance to have it here, 5% chance to have it here, 5% chance to have it here. And look, now the amount of rejections, it's 17%. So in 17% of the cases, I ran it 47 times, and in 8 out of 47, I rejected null hypothesis. I expect to have it 5% here. You can, of course, say that this is too little. So if I continue and then, for example, have at least 100, well, of course, when you have 100, you do not expect to see 5, but maybe you will see 6 or 7%. But look, it never goes below 10%. So now I have more than 100, and it's still the amount of rejections, it's 13%, which is much higher than I expect to see the 5%, right? So this is the multiple comparison problem. What you can do? Well, to solve this problem, to fix this issue, you have 2 possibilities. Either apply another test. For example, in this case, I would run ANOVA test, or for multiple comparison, I would run Toki test for multiple comparison, which accounts for this multiple comparison problem. Or alternatively, you can also use what is called Bonferroni correction. Bonferroni correction is when you decrease artificially the alpha, the significance level, in every single test to make sure that the alpha for all tests will be 0.05. So usually what we do, or what Bonferroni correction does, it simply divides alpha to a number of tests. So in this case, instead of 0.05, I will use 0.05 divided to 3 in this particular case, in this particular case, in this particular case. But all overall, the significance level will be 5%. Let's check this. So you can see I have this little switcher here, which is called correction. And if I click on, now you can see that the alpha for each single test is 0.017. That means that I do not compare with 5% anymore. I compare with 1.7% here, 1.7% here, 1.7% here. And where this 1.7% came from, it's simply 5 divided to 3, right? So it's approximately 1.7. Let me show you an effect of this. Again, I will, if I click a lot of times, and then if I have, for example, 100 cases, you already can see now that the amount of rejections is very small. It's smaller than 5%. So if I keep going, you can see that sometimes it's a bit 5, larger than 5, sometimes a bit smaller than 5. If I keep going and, for example, take thousands of samples, it will be 5%. And you can see clearly the effect of the correction, right? So Bonferroni correction is one of the possibilities to solve this issue.